So the key idea of the paper is to process directly implicit neural representation to perform tasks on the signal contained in this implicit representation without accessing the signal, so without reconstructing the signal. So just processing the weights of the neural network and perform some task on it.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper Deep Learning on Implicit Neural Representations of Shapes, also known as INR2Vec. This paper was published in ICLR 2023, and I am happy to host the first author of the paper, Luca De Luigi. Hello and welcome to the podcast. Can you introduce yourself?
Thank you for having me on the podcast. It's really nice to be here. My name is Luca. I'm currently in Italy and where I was born, in Bologna. I did my PhD here. I just finished it 2 months ago. Now I'm a computer vision researcher in a young startup here in Bologna called iCan. And I've been working on this stuff for a long period, so I'm pretty happy that my PhD was finished with this publication.
Excellent. And who are the co-authors of the paper?
So the co-authors are all people from my previous lab in Bologna. It's called the CV Lab for Computer Vision Lab. I think it's pretty standard. And so we have Adriano Cardace, who is currently a PhD student, really talented, really, practical guy working really hard to get the results. Then we have Riccardo Spezialetti, who at the time was a research fellow, and I can just say that he was kind of my teacher for a lot of stuff about geometry and 3D geometry and how to process point cloud meshes, voxel grids. So I'm really thankful for all the help that I got from him. Then we have Pierluigi Zamramirez, another research fellow. He's currently looking forward to become professor in the university, I think. So he's really a nice guy, and we had a lot of great collaborations together. And then we have my two supervisors, Professor Samuele Salti and Professor Luigi Di Stefano. I can just say that they are the best advisors that I could have asked for. So they were really, really helpful during all my PhD, and especially during this project, which was quite long, I would say maybe a couple of years long. And so they were really supportive and really helpful during the process.
Great. Okay. So let's start talking about the paper. So in a TLDR kind of format, 3-4 sentences, what is this paper about?
The paper is about processing the signal contained inside the implicit neural representation without accessing directly the signal, but just looking at the weights of the neural networks that implement the implicit representation.
So there are a lot of kind of jargon keywords that maybe we need to break down a little bit, but we'll do it in the next section. But before we do, maybe let's talk about related works. So which one or two papers would you recommend new PhD students to read before reading your paper?
So, of course, you need to understand implicit neural representations. And so probably you should start reading the seminal works like Deep SDF or Occupancy Networks or maybe Siren. So all the first attempts to represent continuous signals with neural networks, so that you can understand properly what we mean by saying implicit neural representation, because implicit representation were something that was known already, I would say, maybe already 20 years ago, but just recently, maybe 3 or 4 years ago, we started using neural networks to approximate these implicit representations. And so you need to understand properly the idea of a neural network, possibly a small neural network, approximating a continuous function. And this is what we call implicit neural representation. So probably DeepSDF, occupancy networks, and Siren could be a nice start.
Sure. For those that don't know these words, and this is going to be like the building block that we will be talking about for the rest of the episode, is what are these implicit neural representations, right? So let's say you have a point cloud as input, you feed that into a network, and you get as output some sort of function value for that point in space, right? So you feed a point, you get a function value. So usually it's either like a signed distance function or an unsigned distance function or an occupancy field, right? But the key idea here is kind of have a discrete representation as input and get a continuous representation as output. So you kind of map the entire 3D domain, right? So XYZ input, scalar value output functions, and you model that using a very small neural network, usually using a multi-layer perceptron with either a ReLU or sinusoidal activation in the case of Siren.
Yeah, that's true. And if I can just maybe add something is what I find really interesting about implicit neural representation. Maybe we can start saying INRs for simplicity. So what is really interesting about INRs is that is what you're saying. So we can decouple the memory requirement, that is just the weights of the networks, possibly a small networks, from the resolution of the approximated signal, because we are approximating a continuous function. So theoretically speaking, in output we can have what we call an infinite resolution, and so we have decoupled the memory occupancy of the representation from the resolution of the represented signal. And this is quite interesting because you were mentioning point clouds, and point clouds are a discrete representation. So we are discretizing this function, this 3D function. And if you want to have like a high resolution of the representation, we need to increase the number of points that we use in the point cloud. So we are using more and more memory. And to get an infinite resolution, we need an infinite number of points. So, of course, this is not possible. While with INRs, this is at least theoretically possible.
And also, a continuous representation, you get all the benefits of a continuous representation. Like you can compute first derivatives, second derivatives, which in geometry relate to the normal vectors and the curvature and so on. But let's go back to, you wanted to mention maybe another related work, and I kind of interrupted you. So
no, maybe I would just say that you could also read something about standard 3D geometry with neural networks. So maybe you could read PointNet to get, let's say, to understand how neural networks can process point clouds. Or maybe you can read, Meshwalker to see how neural networks can process triangle meshes, which is really a complicated process. And if you're interested in some contemporary work, I need to mention From Data to Functa, this paper from Emilien Dupont and others, which is really a similar idea to ours in a different context, I would say, in a different implementation maybe. And it's something that came out approximately the same period of time of our paper, so maybe you should also consider that.
Excellent. I'll make sure to put links in the episode description. Okay, let's dive into the introduction. What problem is this paper addressing?
So I would say that maybe it's not exactly a problem, but it's maybe something that we thought of by maybe looking at the future. So we were really, let's say, enthusiastic about INRs, and seeing that many researchers were working on INRs, on getting better and better quality of representation with INRs. But we asked ourselves, so what if at some point we all agree that INRs are a very good representation, and we have all these advantages about continuous representations, and we want to deploy this form of representation as, let's say, the only way to represent 3D data. So what if instead of deploying on the web point clouds and meshes, what if we deploy the weights of the INRs as the standard, let's say, as one of the standard format to represent shapes? Uh, uh, if that's the case, then if we want to perform some task on these INRs, let's say you want to classify the shape represented as INR. Right now, you need to extract the discrete shape from the INR. So you need some usually very slow algorithm to extract the point cloud, for instance, from one INR, or one triangle mesh from its INR. And then you can apply some standard machinery on this point cloud or triangle mesh. But this process obviously is very slow, and and includes a lot of overhead that could be not necessary if there was a way to process directly the weights of the INRs. And so we ask ourselves, can we process directly the weights? Can we perform some task directly on the weights of the INRs without any need of sampling the signal from the INR? And the answer in our case was INR2Vec.
Yeah, I think this is a very interesting observation about your work. You're basically saying, well, there have been several years now that people have been trying to solve different vision problems directly from the signals, right? So point cloud classification, mesh classification, segmentation, or voxels, any kind of input signal. People have been trying to solve the problem directly on this representation. But now with the emergence of INRs, you're saying, well, it seems like it has a lot of benefits because it's continuous, etc. So why not try to process it directly instead of going back to the original signal? I think that's a really interesting point. And so what are the main challenges though here?
Let's say that to name a few, because there are many challenges, to name a few, maybe the first one is that when you consider one INR, typically you have I would say around 1 million of parameters, 1 million of weights of the INR. Let's say maybe sometimes 500K, sometimes 1 million, sometimes 2 millions. Okay, and so the naive approach of processing directly all the weights is really not feasible, and it is and cannot scale to let's say to any kind of input size, because of course if you want to approximate a complex signal, you need a bigger INR, and so bigger means more weights. And so if we process directly all the weights, at some point we cannot scale anymore. And so we at the very beginning we decided that this was not the way to go. So somehow you need to find a smarter way than naively processing all the weights. And this is maybe the first challenge. And other challenges includes the fact that neural networks are black boxes, as we know, and it's really difficult to give some meaningful or semantic interpretation to the weights of neural networks. And so any kind of processing or any kind of let's say manipulation of the signal contained inside the one INR directly on the weights, it is not possible, because of course we have these 1 million parameters and we have no clue on where to change something, where to put something to have some impact, some let's say controllable impact on the signal. So maybe these two are the biggest challenges, I would say, right now.
Yeah, I have to agree. Yeah, this kind of like the INRs, all of the weights, it's infeasible to just process them with just a single fully connected neural network. And on the one hand, there is some structure, but there is also a lot of symmetry within those weights, and anything anybody wants to design has to kind of take into account all of these different constraints. That brings me to the contribution of your paper. So what are the main contributions of this paper?
So the way that we addressed this issue was by, let's say, implementing this representation learning framework where we learn to compress, to squeeze, let's say, all the weights of an input INR into a small compact embedding. And this is the core part of INR2Vec. So we have this encoder that is capable of taking just the weights of the INR and to squeeze them in a small compact embedding. And then once we have this small embedding, we are talking about 1,000 features, so pretty small, then we can apply any standard deep learning machinery directly on this embedding, which is small, is compact, and we already know that deep learning can process this kind of small embeddings. And so we went from 1 million parameters to 1,000 feature vector, and then we can do every task that we can do with the standard deep learning machinery using this proxy vector instead of the whole set of weights.
Yeah, this sounds super interesting. So let's dive into the approach now. So how did you do it?
So what we did is to build this sort of encoder-decoder framework. So we have this encoder, which is based, I would say, on something similar to PointNet. So maybe this is another reason why you should read PointNet before reading this paper. So the encoder is basically a set of fully connected layers that progressively maps the input weights into higher dimension spaces. And at the end, we just use max pooling to compress all the higher feature representation into this small compact embedding. And after that, we use this embedding as input for our decoder, which is based on DeepSDF. So another reason why you should read DeepSDF. And this embedding produced by the encoder acts as a condition for the decoder, which is again is a maybe I don't want to go too technical, but the idea is that this decoder is a network that is capable of predicting an implicit function. So in input to the decoder, you have the embedding of the INR produced by the encoder, and then you have maybe a 3D coordinate, so X, Y, Z. And the decoder is trained to predict the implicit function at that point based using as condition the embedding. And so maybe it is, of course, a not conventional encoder-decoder, because in input you have the weights of the INR, and in output you have the implicit function approximated by the INR. So it is not directly decoding the INR itself, let's say, but we found out that it was quite effective in learning properly this embedding space. So it was really useful to help the encoder to learn this process of squeezing the input weights into a small embedding space.
Yeah, okay, let me just quickly recap, because there are a lot of different building blocks that maybe we need to kind of break down a little bit for our novice listeners. So the first step is actually taking a signal and encoding it into INRs, right? So you have, let's say, a point cloud, you train an INR, now you have a set of weights that you learn for this INR representing the continuous shapes that the points were sampled on. These weights are now the input to your encoder, right? You mentioned that it's a PointNet type structure, but yes, you're actually not feeding points in, you're feeding the weight matrices, right? Then your encoder takes those weight matrices and creates this single vector embedding vector, right?
Yeah, that's true.
So that's like the first part, like encoding everything into a vector. Now you want to get this vector to be able to kind of reproduce the original, let's say, sign distance function or INR output. So you feed the vector with a coordinate and you get a scalar value saying, well, this point is this distance from this shape.
That's perfect. Yeah. It looks like you are one of the authors of the paper. So
I read the paper. Yeah. It's a very interesting approach because you're basically saying kind of reconstructing the INR kind of helps learn a better embedding that you're going to later on maybe use for some downstream tasks. So what are the next steps?
The next steps is using these embeddings for, let's say, as input to other, let's say, networks or other algorithms to perform downstream tasks. So in the paper, we tried a bunch of stuff. So we tried shape retrieval, starting from the embeddings. We tried the shape classification. We tried shape segmentation, let's say. And we tried also a bunch of, probably we could say, generative stuff. So we tried the shape generation, unconditional generation. And we tried also to perform some mapping between embeddings of one kind of INRs to embeddings of other INRs. So let's say we have the embeddings of partial shape and we have the embeddings of complete shapes. We found out that we can learn a mapping to go from the partial shape to the complete shape, always working just on the embeddings. And also, if we have the embedding of point clouds, so let's say discrete surfaces, and we have the embeddings of meshes, so complete surfaces, we can also learn a mapping between these two embeddings. So we can go from point clouds to complete surfaces, only working on these small embeddings. So maybe we can go in details later, but of course, my point is that these small embeddings produced with our approach can be used in a lot of tasks. So classification, generation, retrieval, segmentation, a lot of different stuff where we use this embedding as proxy input for the complete INR.
Yeah, I think let's for a minute choose one of these applications. I think classification would be kind of the easiest thing to grasp, right? So
sure.
So now you have your input INRs, you feed them into your encoder, you get your embedding vector. Now you take that embedding vector and in the classification setting, what do you do with it?
So in the classification setting, we do something pretty easy. So we have this classification network, which is just a fully connected network. So a multi-layer perceptron with a couple of fully connected layers, which takes in input one embedding. So it is 1024 feature vector, and in output predict the logits for the classification task. Simple as that. So, and just we train it with the standard cross entropy loss for standard classification task. So
right, and the training stages are separate, right? You first learn the embedding using the encoder decoder structure, and then for every downstream task, you just take the embedding as is and train whatever task specific network that you need. So in the classification, you just train that classifier kind of structure.
Yeah, that's true. And then maybe it is important to explicitly say this because this may be something that can be a source of confusion. And these two steps are really separate. Okay, so the representation learning step, where we train the encoder and the decoder to learn these embedding spaces. So the objective of the representation learning step is to train basically our encoder, so INR2Vec encoder, to do this, to map the input weights of the INR into a small embedding. And that's it. After that, you can use the frozen encoder to obtain the embeddings for, let's say, any input INR. So you get the input INR, use the frozen encoder, you get its embedding. And then you have the second step, which is your downstream task. In this case, the classification task. You just take the embedding and you feed it to the classification network. Okay, so these two steps are always separate. So the encoder is never trained together with the classification network. First, you train the encoder, and then you train the classification network or the segmentation network or whatever you're training for the downstream task.
Okay, so that was classification. I think it's the most straightforward one. But one of the applications that you mentioned, which I think is very interesting, especially with the rise of all of these kind of text-driven approaches, is when you do things in the embedding space, right? So you mentioned moving between different types of representation using this embedding. So can you elaborate on that a little bit?
Yeah, sure. So the point is that these proxy embeddings, these small embeddings, are suitable both as input but also as output of standard deep learning machinery, because we know that fully connected networks or also convolutional networks can easily produce in output compact embedding and can easily take in input these embeddings. So we performed a couple of experiments where we train a fully connected network. So again, a simple multi-layer perceptron with, I think, 4 fully connected layers to learn a mapping, what we call a transfer function between 2 embedding spaces. So we have one embedding space of one kind of INR. We have one embedding space of another kind of INR. So embedding space is obtained with our encoder. And we learn a transfer function from one embedding space to the other. So one experiment in the paper is point cloud completion, meaning that we have the set of INRs of incomplete or partial point clouds. So maybe you have this, standard airplane without a wing, and you have its corresponding INR. And you use the INR2Vec encoder to get the embedding. And then you have the embedding of the INR of the complete airplane, so with both wings. And then you can just learn this transfer function between the input embedding and the output embedding. And you do that for a lot of samples, of course. You do the whole training. And at the end, you have this learn transfer function between 2 embedding spaces. So you get an input to the partial point cloud and the partial INR, let's say. You get the embedding. You apply this simple transfer function, and you get the embedding of the complete shape.
Yeah, so I think this is really interesting because it kind of starts exploring the embedding space. So have you tried to do some interpolations in the embedding space and see, like, does the reconstruction, or can you reproduce meaningful shapes that, let's say, weren't in the original INRs?
Yeah, true. So let's say that we don't want to have a super accurate reconstruction capabilities from the INR2Vec decoder during training, because the goal is just to train the encoder to get these embeddings. But at some point we started looking, as you said, at this embedding space. We start asking ourselves, okay, how good is the embedding space? Do we have some interesting properties? And we observed that actually the decoder can properly reconstruct the input implicit function. So just starting from the embedding produced by the encoder, the decoder can reproduce the input function with really good quality, I would say. So this encoding decoding scheme is working quite good. And apart from that, you get this nice, I would say, nice property of having a continuous embedding space. And we found out that you can do some linear interpolation between embedding, and you get meaningful shapes during the whole interpolation, let's say. And also all this experiment about learning and mapping between spaces, and maybe also the other experiments about shape generation just in the embedding space. I think that they prove that the space is continuous and it's somehow controllable, and that is usable in input and in output for many tasks. So without imposing any specific constraint on the structure of the space, INR2Vec is already capable of producing this embedding space with nice features, I would say.
Yes, so we kind of already dived into all of the experiment section of the paper. And I guess it's worth mentioning that basically you evaluated the performance of the method based on each individual task, right? So for classification, you did classification accuracy, right? You had model net 40, shape net, all of these kind of standard data sets for this specific task. And I guess the next question is, so are there any specific interesting fail cases?
As you can see from the numbers in the paper, we are usually a little bit far from state-of-the-art results. So when we perform downstream tasks on the embeddings, we are still not able to get the best performances. So both, I would say, in all the tasks. So classification and parse segmentation and also maybe also retrieval a little bit. So you can see that the numbers are saying that all these really specific architectures like PointNet, PointNet++, DGCNN, all these networks that were studied and designed to work on the discrete representation, so directly on point clouds and meshes, they are still superior in performances to our approach. And this is something that we need to study to understand how we can fill this gap. Because, of course, it's something that we want to. Okay, it is cool that we can perform downstream tasks on INRs, but we also want to achieve the best performances, of course. And this is maybe the biggest failure case, I would say. But apart from that, of course, learning this encoding decoding scheme, as we know from other contexts, it is something that is non-trivial. So it's not so easy to learn a perfect encoding decoding scheme, and sometimes you can see some failure in encoding one shape. It's not like a catastrophic failure, but you can see that maybe sometimes some small detail of the input signal are lost in the encoding decoding scheme.
Yeah, I have to say, referring to your first point about not achieving the state of the art compared to the discrete representation, that to me this was really surprising, because INRs are supposed to represent continuous functions, right? And continuous functions have more information than those discrete representations. And theoretically speaking, this should provide more information for any network to learn and be able to perform better. And I guess the big question here is why. And when I read the paper, I was thinking, well, maybe it's the embedding space, maybe it's too dense, maybe it was larger, maybe it's the architecture that kind of doesn't, extract all of the relevant information to kind of condense this to this one vector. And I think this is a really interesting point to start further research from. So how can we get this to outperform the discrete representation like it should?
Mm-hmm. Yeah, I totally agree with you. So the point is that all these experiments, so creating the data sets of INRs and training INR2Vec and so on, was quite a long process. So our goal was to perform as many experiments as possible to see if actually INR2Vec embeddings could be used as input or output for a lot of different tasks. But we didn't have the time to explore, let's say, depth-wise every single task. So as you say, probably the best idea would be to take one task, let's say classification, which is maybe the easiest one, at least as setting wise, and try to understand what's going on there. And you could be right. It could be that the embedding space is too dense, so maybe increasing the feature size of the embeddings could already help a little bit. It is possible that, of course, the encoder structure, the encoder architecture can be improved to extract maybe all the, let's say, tiny details of information that right now maybe are lost during the process. So, of course, there is a lot to do, and I think that a lot of interesting research can start from here.
Yeah, I think these open questions are super important, super interesting, right? Young PhD students usually think, well, yeah, I'm doing a paper, I'm going to solve all of the problems of the world, every question will be answered. But actually, the interesting papers are the ones that maybe open more questions than the ones that they answer. And I think the nice thing about this paper is saying, well, look, we can do this. Now it's up to the rest of the community to come up with how should we do this so it actually works perfectly. And yeah, I think maybe it's the INR encoding that you do in the first place that maybe that's what's missing. Maybe it's missing the detail. Maybe it's missing something else. Because I don't know how many of the listeners can actually appreciate, right? So training for me on my local machine with my A5000, training a siren from a point cloud takes about 2.5 minutes, right? So now you want to encode a data set that includes 12,000 shapes. That takes a long time, even if you parallelize it and all those kind of things. So yeah, every data set that you take, just converting it to the right format takes a long time because you need to train all of these INRs. And if you want to check if the INR is the problem, you have to retrain it. And that's a lot of resources.
Yeah, exactly. I mean, so another interesting direction is to speed up the INR training process. Okay, and it is actually an orthogonal direction to INR2Vec, because INR2Vec start from the assumption that we already have these data sets of INR. Okay, and of course, in my experiments, I had to create them because right now we don't have big data sets of INRs. But in the main assumption of INR2Vec is that in the future we will have these big data sets of INR. Okay, so of course to obtain and to be able to use INR easily in a real world application, we need a super fast way to train them. Okay, and it is quite interesting that in the last year maybe many technologies came out, I don't know, Tiny CUDA to name one. So this CUDA optimized implementation to train this MLP to obtain INRs. So we already have a lot of researchers working on this topic, but I think that there is some margin to still improve the INR training process. So this is already another interesting direction.
Okay, so moving on to the conclusions and future work section. So how do you see the impact of the paper going forward?
For sure, I mean, there is a lot to do, and we need to be clear about several points because, as I already mentioned, we are not able to achieve state-of-the-art performances. So this is, as we said, something that must be studied, and of course, we need better ways to obtain INRs and to, let's say, also be able to manipulate INRs, because another big problem of the process was creating, let's say, all the augmented version of the INR, because as you know, when we train deep learning networks, usually we use some data augmentation to avoid overfitting. And when you have the point cloud in input to your network, it's quite easy to rotate the point cloud or scale it or translate or whatever. While if you have in input the INR, so the network, representing the point cloud, there is right now no way to directly rotate the point cloud contained inside the network. And so we had to perform all this data augmentation offline to create these big data sets and avoid overfitting. And for future work, this could be something that must be resolved. And apart from that, apart from these, let's say, technical problems, of course, I think that for future work, and we are already somehow working on this, is to extend INR2Vec to other signals that are not the 3D shapes. So to use INR2Vec on INRs representing images, or maybe also video or audio signals, and maybe most importantly to neural radiant fields, because right now there is a lot of interest in neural radiant fields, and being able to use INR2Vec on these kind of networks could be really useful, because let's say that for 3D shapes, we already have all these standard machinery working on the discrete representation, so working on point clouds, working on meshes. But if you think about radiance fields, there is no way to process some discrete representation of the radiance field. So we have just the INR in that case. And so we really need something like INR2Vec or a similar approach to perform some task directly on the INR.
Yeah, I completely agree. Those radiance field, the nerve kind of papers, so they kind of combine all these different type of signals, right? They do have the 3D baked in there, and they have the color information, and it makes sense that would be super useful for any downstream task. And it really seems like the field is going a lot in that direction. So yeah, definitely a good direction to further explore how INR2Vec can be implemented on this. All right, so moving on to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comment you had in the review process.
Okay, so the review process was really nice, in my opinion, because all the reviewers, we had, I think, 3 or 4 reviewers, I don't remember exactly, but they were really, let's say, interested in the paper, and they expressed a lot of interesting thoughts on the paper. So they raised a lot of concerns about the usability of the framework in, let's say, real-world applications, and they raised some concern about the fact that in the future INR will be a standalone representation for shapes or for other signals. And so at first they were not super convinced about the possibility of using INR2Vec in concrete applications. And another big concern from reviewers was the fact that a key point in INR2Vec is the use of the same, let's say, weights initialization for all the INR in input to INR2Vec. So what we found really important was to start the training of every single INR that composed the dataset from the same initialization. And this was seen by the reviewers at the beginning as maybe a drawback of the method, and maybe a too strict requirement for the deploying INR2Vec in the wild, let's say. But then, we were able to build a very useful discussion with the reviewers, and we found out that, from a practical point of view, we just explained that we already use the same initialization for a lot of tasks. Every time that you, download a ResNet from PyTorch or from TensorFlow, you get the pre-trained weights from ImageNet. Now, this is pretty standard in every task. So if at some point people decide to use INR2Vec, I think that it is not a big problem to use the same set of weights to start training the INR. And also, starting from that, we digged a little bit into some technical details to understand why the same initialization was needed. And we found out that it was a very easy way to obtain what is called linear mode connectivity between the weights of multiple neural networks. And this was really, a nice result from this discussion process, okay? Because it was something that at the very beginning we were not aware of, and to answer to the reviews, we found out this part of the paper that you can find in the appendices, and this was really a nice result of the review process. And the last thought is that it was very nice to see that the reviewers were open to the discussion. They were answering to our questions, and there was a nice back and forth between them and us. And at the end, they also raised their initial score, the initial rating, so the paper was accepted. So, for me, it was really a nice process from the beginning to the acceptance.
Yeah, I have to. So regarding the initialization point that they raised, I have to say, yeah, it's completely understandable, right? The INR domain is a little bit different than other domains because it already has been shown that, for example, geometric initialization can benefit the convergence of these type of networks, and you get better reconstructions, better INRs if you use a specific type of initialization. But it's a valid point to raise, right? Because it kind of you would think that it would limit maybe the generalization of that method, but I don't think, sure, it has a usability question, but not a novelty question, right? Because it doesn't, the novelty is still there. And it's really interesting the fact that there was a discussion. So not many people know that for ICLR, it's actually a discussion period. It's not just a one-page rebuttal that you kind of submit and you hope someone would read and that's it. Like the fact that there is a discussion, you, as you said, you can learn from this process and the paper just gets better.
Yeah.
Super
absolutely. Yeah, absolutely.
All right. Is there anything else you want to mention that we haven't covered?
I don't think so. The paper is quite long in the end. So, during the process, we added a lot of appendices. So I just can say, if somebody is really interested, maybe they should read all the paper, and maybe they shouldn't be scared about the 40 pages of the whole paper, because there are a lot of details that need to be discussed. But apart from that, I think that we covered the main aspect of it, so it's fine for me.
Great. Okay. So, Luca, thank you very much for being a part of this podcast. And until next time, let your papers do the talking.
Are you interested in 3D and AI? If so, the team at Yume is interested to hear from you. Yume is an Israeli startup dedicated to volumetric video creation. They were voted as the 2022 Best Startup to Work For by the Duns 100. Join their team that works on geometric deep learning research, implicit representations of 3D humans, NeRFs, and 3D 4D generative models. Visit yume.com. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.